The topic that we're going to explore this week is why does the wind blow? And the first part of the answer to that question is that the sun heats the earth unevenly. And there's three reasons for this. The first is that different materials on the Earth's surface have different specific heat capacities, which is to say some parts of the Earth heat up faster than other parts. The second reason is that the color and the texture of different surfaces of the Earth absorb and radiate heat better than other surfaces. And lastly, the angle of insolation from where the sunlight is hitting the Earth affects the temperature of the air above that surface. Now we're going to explore each of these three in a little bit more depth. First, consider how color and texture affects heat. The dark, rough surface on the left, where the forest is going to absorb and radiate heat better than the light, smooth surface where the snowy field is on the right. And remember that as the temperature increases, the air's pressure and its density decrease. So above the dark, rough surface, the air is warmed and it becomes less dense, and above the light, smooth surface, the air is cooled and it becomes more dense. The less dense air rises as the cool, more dense air sinks, and that also means that the warm air has a low air pressure while the cool air has a high air pressure. Now the rule for wind is that wind is the movement of air from high to low pressure. And you can think about this like a skateboarder going down a ramp. The skateboarder is the wind, and the high point on the ramp is like the high air pressure, and the low point on the ramp is like the low air pressure. So air always moves from high to low pressure. Putting it all together, above that dark, rough surface we have warm air that is low pressure and low density, so it rises. As it moves away from that heat source, it cools down. The cool air sinks back down and it creates cold, high density, high pressure air on the surface above the snowfield. The wind blows from the high pressure to the low pressure and it completes the convection cell. On this isographic map you can see what's called a high pressure center, which is surrounded by circles of lower pressure. The air again is moving away from high pressure to low pressure, so it's blowing outward from the high pressure center. And also notice that just like when we learned about topographic maps, the pressure gradient is steepest where the lines are closest together, and that results in the fastest wind. In this example we have a low pressure center. How would the wind move on this map, and where would the wind be fastest? Well, in a low pressure center, wind is blowing inward from a higher pressure to the lowest point. And notice also that where the lines are closest together, I've outlined in a red box. On page 13 of your reference table, there are these symbols for how wind is portrayed on a map. The line coming off the circle shows which way the wind is coming from, and then the little lines coming off of that indicate the speed of the wind. Wind is measured in a unit called knots, and a full feather equals 10 knots, and a half feather equals 5 knots. In the rest of this video we're going to explore wind on two scales. Local winds are winds that can change quickly from daytime to nighttime, and they are winds that are affected mostly by landscape features. Global or planetary winds are affected mostly by latitude. Hi everybody. We are here at Third Lake in Old Forge, which is in the Adirondacks, and we're going to talk about local wind patterns today. So you know what that means?
No.
That means we're going to build a fire. Okay, this is a wet piece of newspaper because I really want you guys to see the smoke. It's going to make the fire really smoky. Alright, now notice that the lake is over here and the land is over here, and right now it's the middle of the day, and what's happening is the smoke is clearly blowing from the lake to the land. And we always name wind after the direction that it's coming from. So this is called a lake breeze or a sea breeze, because it's coming from the lake or the sea. Now let's find out exactly why the wind is blowing from the water to the land. Land heats up and cools down faster than water because it has a lower specific heat capacity. So when the sun is shining down on both, the land heats up first and the air above the land becomes warmer, lower density, and lower air pressure. Above the water, the air has higher pressure, higher density, and it's cooler. So the wind is going to blow from the high pressure above the water toward the low pressure above the land, and this is known as a sea breeze. Alright, we're here at the same campfire location that we were here earlier, and now you can see that the smoke has actually changed direction. So it's coming from the land to the water. Now let's take a look at exactly why the wind has changed direction. At nighttime, the land cools down faster than the water because it has a lower specific heat capacity. So the high pressure is now above the land where the air is going to be cooler and more dense. Above the water, which holds on to its heat longer, the air is going to be warmer, lower pressure, and lower density. So now the wind is going to blow from the higher pressure above the land to the lower pressure above the water, and this is known as a land breeze. We've learned previously that the low latitudes near the equator receive more high-intensity insolation from the sun than the high latitudes towards the North Pole and the South Pole. Now, because of that, the air pressure above the low latitudes is low pressure, and the air pressure above the high latitudes is high pressure. So we would generally expect wind to blow from the higher pressure near the poles toward the lower pressure near the equator. But it's a little bit more complicated than that. Notice that there is in fact low pressure at the equator and high pressure at the North Pole and the South Pole, but there are also two other belts of low pressure latitudes and two belts of high pressure latitudes. Wind is going to blow from high to low pressure, but sometimes that means that the wind is blowing north and sometimes that means that the wind is blowing south. Now there's a problem with our model, and that is because winds never actually blow to the north or to the south. They are deflected to either to the right or to the left because the Earth is rotating. This is known as the Coriolis effect, and this little video here will explain this a little better.
Convection currents are pretty straightforward, but because we're dealing with planet Earth, we have to add a spin to it.
Earth's rotation, that must change the convection currents.
It does. We can use this globe to show how the rotation bends or deflects the currents. Try drawing a straight line from the North Pole to the equator.
They all curve the same way.
This is known as the Coriolis effect. It drives the three dominant winds on our planet. The trade winds, the westerlies, and the polar easterlies.
And here at the equator, there aren't any winds?
No. Along the equator, there are no prevailing winds. This is where we find the doldrums. Do you know which winds drive our weather?
Most of our weather systems come from the west, so they must be driven by the winds from the west.
Right, the westerlies.
So notice that in the northern hemisphere, all the winds are deflected to the right, and in the southern hemisphere, the winds are all deflected to the left. So this is how the whole thing looks in your reference table. Notice that it doesn't actually list high and low pressure at the different latitudes, but it does indicate wet latitudes and dry latitudes. Wet latitudes indicate increased humidity, which basically means low pressure, and dry latitudes indicate decreased humidity, which basically means high pressure. So the other terms that we need to know that are related to the Coriolis effect are cyclone and anticyclone. An anticyclone is a high pressure system where the winds blow outward in a clockwise direction, and notice that they're all deflected to the right. A cyclone is a low pressure system where the winds are blowing inward and they're moving in a counterclockwise direction. And finally, you can see in this 3D model of the same cyclone-anticyclone system that the anticyclone has sinking air while the cyclone has rising air.